This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Good afternoon. On behalf of the Graduate Council of the Academic Senate, it is my very great pleasure to welcome you today to the first of two Hitchcock lectures to be given by Professor Harold Kroto. The Hitchcock Professorship is one of the earliest endowments at the University of California at Berkeley. It was developed from a bequest of property made in 1885 by Dr. Charles M. Hitchcock, a San Francisco physician with a long interest in education. As stated in his will, the purpose of this bequest was to establish a professorship at the University of California for the purpose of giving free lectures on scientific and practical subjects. The fund was allowed to accumulate until 1909, when the Hitchcock Lectures were instituted with the inaugural lecture of a distinguished chemist from the University of Chicago, Julius Stiglitz. The university received an additional gift in 1930 from Dr. Hitchcock's daughter, Mrs. Lily Hitchcock Coit, best known as the donator of funds to build Coit Tower in San Francisco. Mrs. Coit directed that the professorship made possible by this enlarged endowment be designated the Charles M. and Martha Hitchcock Professorship in memory of her parents. The great extent to which this endowment has enabled the faculty, staff, and students of the university, and the general public as well, to become closely acquainted with distinguished scholars from throughout the academic world is evident by the list in your programs of those who have served as Hitchcock lecturers and Hitchcock professors. We are proud to see a long tradition of Hitchcock professorship so eminently upheld by a scholar of the stature of Professor Kroto. In 1996, Professor Kroto was awarded a Nobel Prize in Chemistry for the 1985 discovery of a previously unknown class of carbon molecules, C60, to be called buckminsterfullerene. These and similar molecules were dubbed fullerenes or buckyballs because their genetic and molecular structures are suggestive of the architectural domes designed by our Buckminster Fuller. Since then, chemists have synthesized some 5,000 variants of buckyball, including elongated spheroids, sheets of carbon, and microscopic tubes, opening a universe of possibilities that is based on how nature bonds carbon atoms together. These tubes are believed to have greater tensile strength than anything yet made, and their electrical conductivity will rival that of metals. Professor Kroto was born in 1939 in Lewisbeck, Cambridgeshire, and attended the University of Sheffield. He received a bachelor's degree in 1961 in chemistry and a PhD in 1964. Since 1967, he's been a faculty member of the University of Sussex, where he is currently a Royal Society research professor. Among his many other honors has been his election to fellowship in the Royal Society in 1990, he received the Hewlett-Packard Europhysics Prize in 1994, and a knighthood in 1996. Without further delay, I'm pleased to present to you Professor Kroto, whose lecture topic today is Science, a Round Peg in a Square World.
Well, I've only just looked at the list of people on here, and I hope it isn't come down after seeing all these fantastic scientists, people who've made some great contributions. Anyway, now this is the worst lecture you'll probably get. Anyway, it's a great pleasure to be here in California, particularly at Berkeley. I've been here many times, and normally I give a lecture, as Rich Safely knows, to his freshman chemists. This is a bit of a different one. Since I got this prize, people think that what I have to say is important. Now I can prove that it's not true. I'm not going to talk about this today. I'm going to talk about more polonium things slightly. It's a fantastic molecule. What I'd like to do is, I said this will be my pontification talk, and you know what writers, as soon as they get it, they start pontificating, right? don't take any notice, but still I got a file called Il Pontificatore, and I pulled out this talk from it. What I'd like to do is start with this. One of my favorite people is Jacob Bronowski. I don't know how many people saw the Ascent of Man program. Could you put your hands up? A wonderful set of programs, probably the best set of programs on science that were ever made. He's playing with his grandson, or his grandson's playing, and I wonder how many of you had this toy when you were children. Can you put your hands up? Yeah. How many of you gave it to your children? Okay, come on. I know. The interesting thing is, this child, as you well know, if you were given it, your parents were trying to find out whether you had any brains or not. And if you picked the cube up and put it through the square hole, it made your parents happy. But there was one child, I shan't tell you who it was, but every time he picked up the cube, he put it through the round hole. And when he took some other shape, he put it through the round hole. And the mother got very worried about this and took the child to see a psychiatrist. And the psychiatrist said, it's always the round hole, yeah? That means that it doesn't matter what the problem is, it's always the same solution, yes? He said, yes, doctor. He said, well, the only possible career for this child is to be a politician. Mrs. Clinton. Anyway, essentially, these symmetries are really quite interesting because symmetries and patterns are perhaps the only thing that the brain recognizes. And I think it's deep in our imagination, deep in the human spirit, that an understanding of symmetry seems to reside. For instance, if we look to these objects, which were found in Scotland, they're about 3,000 years old. They're in the Ashmolean Museum in Oxford. And they were found at the site of the first Glasgow Rangers versus Celtic football match. In those days, the spectators used to carve the rocks into nice shape before they threw them at the opposition. It shows that in those days, even the spectators had some feeling of symmetry in patterns. Now, these patterns are platonic structures, and it's interesting. Alan Mackay, fantastic scientist, main famous for Mackay icosahedra, thinks that these were actually carved so that they could put string when you were fishing, maybe some way of wrapping the string up or something like that. Now, these structures were known for a long time, and in the work of Leonardo da Vinci, we see the platonic structures. And also we see something interesting about Leonardo, that he was left-handed in his notebooks, which is perhaps one of the greatest contributions to the culture that has ever been, really not much Leonardo's painting, but his notebooks. We see that he wrote, he's left-handed, and if we turn this over, with modern technology, you can see that the numbers are, in fact, the right way around. Now, these symmetries are not only interesting to Leonardo, but also to Piero della Francesca. This beautiful page of his notebook, where we see the soccer ball structure. And in fact, this soccer ball structure is to be found again in Leonardo's work here, in icosahedron narcissus vacuus, the hollow, truncated icosahedron. Now, in a sense, symmetry is very deep, and it's also involved. I mean, some of you may be curious, and perhaps you aren't aware that there's only one decent chemistry book. It's this one. It's the Tenet of Plato. And if you look at this, you find a statement which is, in the first place, it is clear to everyone that air, fire, earth, and water are bodies, and all bodies are solids, and all solids are again bounded by surfaces, and all rectangular surfaces are composed of triangles. Now, I'm sure that's obvious to everybody. But it turns out that on the basis of this, the 5 platonic structures are the fundamentals of chemistry. Now, we've gone a little bit further than that, but there's an interesting parallel. I started off as a physical chemist and spectroscopist, and one of my teachers was a guy called John Howard, and he pointed out that I should know something about Van Vleck, and you will find here in the work of Van Vleck, read on this one, the great particles. Practically everyone knows that the components of total angular momentum of the molecule relative to the axes x, y, and z fixed in space satisfy these computational relations in this form. Now, I went down Shatter this morning, and I asked him, not a single person knows that it's right. And I'm just telling you, Bert, you're not doing your job, because there are a lot of people here who don't, not a single person, you know, this, and that, according to that, like practically everyone knows it. And I didn't know it, so I thought I'd better find something about this. And in the work, in one of my favorite books, The Theory of Atomic Spectra, of course, there are these computational relationships. And when I understood these for the first time, I realized that they explain basically the whole of chemistry. Because on the basis of those computational relationships, you get the relation 2k plus 1, which is 1, 3, and 5, 1, 3, and 5, and that's the fundamentals of the periodic table. So these symmetries and patterns underlie the whole of chemistry and much of physics. Not only that, in that book, you have to get to page 60, and I'm expecting you all to be able to solve this equation by the end of the lecture. This is a page, and it's Dirac's derivation of the angular momentum selection rule, delta J plus 1. And I think it's beautiful. You don't have to be able to understand it immediately, but to say, yeah, this is a beautiful page, and it's so beautiful it's got to be right, and if Dirac did it, all certainly is right. But in fact, that tells us how we explain how light is emitted from an atom, say, on the sun. Okay. And energy is found as a photon. The photon is absorbed by your eye. It controls the absorption of photons by matter. And in fact, it controls the way in which the light in the screen comes and how you perceive the world. So in the angular momentum, Jet is all the chemistry, and much of this is how you absorb all the information through your eyes. And I think it's so beautiful that I had to learn that, and I had to do that, and ended up, I think, with some understanding. Now, there is a page, my major interest is in graphics and design, and one of my favorite books, and one of my favorite artists is Ben Sharman, and The Love and Joy of Letters. There's a page which I find rather moving, and it's moving in some ways as that particular page 60 you come on shortly. And it's about Franco and Vanzetti, and I thought I'd read it out because I think it's one of the most moving things ever written. Vanzetti was quoted verbatim at the trial of these two anarchists for the murder of policemen, which most people believe they did not do. And if it had not been for these things, I might have lived out my life talking at street corners to scorning men. I might have died unmarked, unknown failure. Now we are not a failure. This is our career and our triumph. Never in our full life could we hope to do such work for tolerance and for justice and for man's understanding of man as we now do by accident. Our words, our lives, our pains, nothing. The taking of our lives of a good shoemaker and a poor fish vendor, all that last moment belongs to us. That agony is our triumph. It's a fantastically moving piece of English, but of course it's not perfect, but it's perfect at the same time. And I'm going to talk about language a little bit later. Okay, that's the introduction. This is about science, and science is, I believe, the dominant culture of the 20th and perhaps the 21st century, even more dominant in the next. And I think it's an understanding of science and where it fits into society which I'd like to deal with. I'm going to quote from John Conforth, one of my favourite people. He's a Nobel Prize winner. He's been dead since the age of 20. He's in Sussex, one of my favourite friends. He talks about chemists. He said, chemists who create new compositions of matter have transformed to an even greater extent in the modern world. New metals, plastics, composites, textiles, adhesives, coatings, and so on. The list is much longer than this. Chemists created the material for them all. A physicist, a mathematician, a biologist, or an earth scientist could tell you a similar story. These are the contributions of the scientists and the technical community to our life. And very recently, I was in Poland in the mines in Biochemistry during the salt mines, and I went down these mines for about 2 hours, and I just thought of what it must have been like in the 17th century. When people spent 12 hours a day, 7 days a week, extracting salt out of salt mines, basically to preserve food before there was electricity and refrigerators, and the place blew up and they had to scratch this out without just pickaxes. Basically, science and technology has freed us from the slavery of just working just to survive and eat in a way that I think most of our children don't realize, and most politicians and other people as well. Scientists are embedded in the fabric of modern society. Most of them spend their whole careers responding to the demands of the state or the market. They are so used
of those who are non-scientists, assume that that is all they are there for. To an increasing extent, this majority is insisting that scientists ought to concentrate more on what society says it wants from them, and as for teachers of science in schools and universities, their business is to train people who will continue to satisfy these demands. This is from the 75th anniversary presentation by John Crawford to the Australian Chemical Society. He was 75 in the same year that particular science report. The problem is particularly stark in Britain for people who are doing science, because if one looks at this statement here by Richard Brooke, Chief Executive of the Engineering and Physical Sciences Research Council, he declared, "I would be suspicious of a scientist who could not explain why the work was being done in the first place." Those are the sorts of things that are being said now about fundamental science. Here's another one, Rob Margetts, a member of the EPSRC users panel, again, people who are in control of financial support of fundamental science. And he says, Rob gets balks when it comes to so-called blue sky thinking or research for its own sake, especially when there are effective means, in ICI's view, of steering its funds selectively to areas of excitement and industrial opportunity. He says, "I am uncomfortable with the idea of blue sky research because it implies an activity with little sense of direction." Now, when I was trying to get a job, I went to ICI, and I went to an interview, and I was told that ICI discovered that it made more money out of the discoveries that were made by others and that they brought in, other than their own research discoveries. So I had an inside track into that particular area. Now, for those people that have something from Tolkien, Lord of the Rings, and this is it, and not all those who wander are lost. Because I think this is the statement for all scientists, because in a sense, science is a wander through the world, for many of us anyway, where we never really know where we're going. But we're doing it with our eyes open, and we like to discover things which are not known. And in many cases, things which you cannot know ahead of time. So what is, it seems to me, the way forward for research? And I'll take this from Lester Thoreau, The Future of Capitalism, a very interesting book. The proper role of government in a capitalistic society in an era of man-made brain power industries is to represent the interest of the future to the present. But today's governments are doing precisely the opposite. They are lowering investments in the future to raise consumption in the present. That is the situation that we find. And I think it's getting more and more serious because the problems that will confront us in the 21st century, I think, are very, very much greater than those that confront us at the present time. One of the great scientists of the 20th century was E.W.R. Stacy, who was the director of the National Research Council in Canada, and he, in his selected works, Babbitt has put them all together. It's a very important document. He says he was implacably opposed to the concept of the scientist as an organization man. He valued in scientists the quality of individuality and independence. The committee and the team worked in the personification of woolly thinking to be abhorred. He resisted all efforts at the bureaucratization of science and insisted throughout that the man was everything and the project was nothing. I don't think it's an accident that most of us who were at the National Research Council of Canada and those within the scientific community looked at the Canadian National Research Council as the one government research council which made a great impact on fundamental science. I think it was due to Stacey's ideas. Now, again, I think this is very important because I'm continually being asked to sit on committees with people who are from totally different areas, and I realise that this is probably more true now than it ever was before. Committees set up to advise on why general areas are of relatively little value in comparison with the committees of experts set up to advise on a particular problem in which they have special knowledge. I feel now more than ever this is a very important thing, and yet with this movement now for large numbers of people to actually talk and pontificate about things they know very little about, which is what I'm doing now, of course, as you well know. However, so that's why I tell the point again, notice. Okay. I think quite a number of things I'd like to say. For instance, I noticed that John Polanyi was here, but his father It's a very famous scientist. He says, like Marty, he believed in the spontaneous coordination of independent initiatives and the exercise of those informal mechanisms which traditionally have been used by academics, the scientific meeting and the expert committee. I think those are fundamental to the way science should be handled in the future. And I think it's possibly subject to discussion. However, that's one attitude that I particularly have. I would like now to discuss, again, the article is from that of John Cornthorpe. For those of you who are interested, is the Royal Australian Chemical Society and University Lecture from 1992 by John Walker Cornthorpe. And I think quotes a very interesting case, which I'd like to suggest is the way that science progresses in some of the most important areas. I know that there's focused science and there's targeted and strategic research and applied science, but this is the sort of research that I think universities should focus on. Here is an actual and far more typical case. Some people decided to examine the effect of an electric field on living cells. They generated this field between two platinum surfaces immersed in the liquid culture medium. The cells died. But the people who did the experiment were real scientists who resisted the obvious conclusion and found that the cells were not being killed by the electric field, but poisoned by tiny traces of dissolved platinum. They mentioned their finding to a colleague who looked for and found a stronger effect on cancer cells. Searching the chemical literature for soluble compounds of platinum turned up a substance that had been made nearly 100 years ago by a chemist in another country whose interest was simply to explore platinum chemistry. This compound was even more effective against cancer cells. In the event, a large number of people are alive today who would be dead but for this constructive but unfocused curiosity of several scientists separated by discipline, nation, and time. The factors combining this success were curiosity, skepticism, good communication, and publication results. In this time of secrecy, this is something that's very important. Together, they produced an outcome that nobody predicted or expected, and that is the essence of the research. But it has always been difficult to persuade those who finance research that predictable results are worthless, and that the best hope is to employ a team that makes the vital connection between other people's results and sometimes their own. That, I think, sums up the sort of research that universities should be doing, and it's becoming, certainly in Britain, increasingly more difficult for us to do that sort of research, which, as I say, is wandering in a world where we are interested in following a pathway, and if it turns down our way, it's interesting, but we don't know where it's going, we're not able to do that. Okay, that's the first part of what I want to say. Tomorrow's lecture will be related in some ways to this, where we ended up in the place which we didn't expect. I've got several hours of lecture. I'm going to start at this point now, because I think it's important to decide how industry and how government and how research actually combine. In Britain, there was an article which started, accountants should not run British industry. And in that article, we found here, Akio Morita, the chairman of Sony, delivered Britain's first innovation lecture a year ago. He said, in Japan, almost every major manufacturer is run by an engineer or a technologist. Someone once mentioned to me that many UK corporations are headed by chartered accountants. This strikes me as very curious. I do not believe they should be at the helm of industry. I think that's true as well. So these are the sorts of situations we find ourselves. The question now is, that's science and technology and industry. What about education? I think this is one thing where the university, Berkeley, has a tremendous record for education. But I'm sure here, as also in Britain, we're facing some problems. And that is that science is now, I think it's a little bit better than it was 10 years ago, but it's still a problem. It's how one educates people in science. The problem, however, is not easy. and is not to be solved by cramming elementary chemistry or physics down the throats of first-year art students. What are necessary are not the efforts of popularizers of science who write semi-fictional articles about its wonders or try to explain the whole of nuclear physics in one easy lesson. The effort must rather be to give some idea of what science is and how it works and its philosophy and its methods. Now, again, that's from the work of Stacy. As general education has increased in depth and become more widespread over the past 7 centuries, the universities have continually sloughed off the more routine items to the schools. With the changing demands of society for educated people, it is vital that the curricula of both schools and universities move forward. Now, believe it or not, this is from 1950, and it seems even worse today than it was in the past. In reality, however, a great deal of worry over present-day education is due to the fact that exactly the reverse is happening. In many cases, as science has become more important to society, the schools have given it less attention, and the university curriculum is obliged to move backwards rather than forward. That has happened in my lifetime to an incredible extent, and it's something that I think we should be very worried about, because as science and technology become more efficient, people become more and more disconnected from the way that science and technology have actually had this immense impact and made our lives so much easier and better. And if we don't solve that problem in the next 10 and 20 years, I think science and technology will be used even more injudiciously in the future than it has been in the past and in the present. So what's the problem? The problem is, I think, in education. Here's an example. Can scientists shake off their mad media image? And we know who this is, and we know why, because who's responsible for this, right? Is it a surprise? Now, this is one of my favorite paintings. It's a wonderful painting by Hans Henny, a Swiss artist. It's a beautiful picture. But we should think about this, because this was Einstein as an elderly gentleman. When in fact, when he created those beautiful theories, this is what he was like, okay? And I think we have to change the perspective of scientists. For instance, when we discovered C60, this was with Bob Kerr and Rick Smalley and Jim Heath and Sean Ryan, it got in newspapers, and here was a picture, a carbon copy of The Secret of Life in a local newspaper, the Brighton Evening Argus. Here is this, and I put it up on the notice board, and someone wrote, "Fantastic likeness, Harold, here you see." Now, when I was here last week, I found this. I hope you can see this. I'm not sure whether you can. But here's this little kid, you see, and this is the perspective. And the problem is that it's not cool to be a scientist at the age of 14. I've given talks here to 9-year-olds and to 14-year-olds and to 16 and 18-year-olds. And the biggest problem is at the age of 14, because it's not cool to be smart as a scientist. Right? And I think that's a critical age, because it's a killer. And the reason is that so few of our really smart kids are going into science and technology, and we desperately need them. And the problem is that the newspapers have this sort of image. I was recently in Spain, and in fact, this is different in Spain. Here is a picture of the Cadiz Información, and here they got me dancing the tango. Naomi Campbell was over here actually, but they missed her off the picture. Anyway, just to show that Spanish had got it all here. The problem is quite serious, and in the Times of London, Simon Jenkins, who wrote a very important article, Alan McKay pointed this out to me. For example, this year the Times published a major article to the effect that the national curriculum puts quite unrealistic emphasis on science and mathematics, which few of us ever need. Now that's a very dangerous guideline, okay? Major article in the Times. I mean, I wonder whether, he should have an open heart surgery without an anesthetic or something like this. He would really need chemistry then. So this is the problem. We've seen science in education, science in newspapers. What about science in government? Well, here's an example. When C60 was discovered, there was a question in the House of Lords. And Lord Harold of Hale asked Her Majesty's government what steps they are taking encourage the use of buckminsterfullerene in science and industry. And there was a discussion after this, and that discussion went on like this. Now, it makes more sense like this than it does if I actually separate it. But it went on. Lord Williams of Melville, how many have read Tolkien? Right? You know, I thought he made up the names, but he just went to the House of Lords, you know. All the characters are in there, right? My Lord, I got a bit of flu, sorry. My Lord, is the noble Lord aware in supplementing his answer that the football-shaped carbon molecule is also known for some extraordinary reason as buckyball? Baroness Sear, my Lord, what correctly in my ears, can the noble Lord say whether this thing is animal, vegetable, or
Lord Ray, my lords, I'm glad the noble Baroness asked that question. I can say that buckminsterfullerene is a molecule composed of 60 carbon atoms known to chemists as C60. Those atoms form a closed cage made of 12 pentagons, and 20 hexagons that fit together like the surface of a football.
my favorite line, Lord Renton, my lord, he is shape of a rubber football. When that question was asked, they looked around for an answer, and there was nobody. And then suddenly, on the chandelier, they looked up, and there was only one person who could tell them what it was, right? Now, it's one of the great delights of my life, and I think the greatest discovery of the century has got to be DNA. I think it may be the greatest discovery of any century. What it will do if it's used judiciously is fantastic. If it's not, it obviously worries. But one of the greatest delights is that my DNA is only about 1% different from this guy. I love the guy's face, right? I feel at one with this fellow. And I discovered also our DNA is only about 50% different from a fruit fly. If you have a problem with being, only 1% different from an orangutan, how much about a fruit fly? They're fairly closely related, similar bits. Anyway, of course, at the end of the day, the House of Lords is going to come to the question, my lord, what does it do? Lord Ray said, my lord, it is thought it may have several possible uses for batteries as a lubricant or as a semiconductor. All that is speculation. It may turn out to have no uses at all. But then, of course, they know what the old Solomon. Well, Russell said, my lords, can one say that it does nothing in particular and does it very well? Well, the answer is yes, it does, and we'll talk a little bit about that tomorrow. But the problem with science is a problem, I think, of language. Primarily, it's interesting. Language is perhaps very fascinating. We learn language by the age of 2 or 3. All right. How many of you most kids can learn language by the age of 3. You don't even try. And then we spend 10 years trying to teach a kid French at school. I mean, it's the most stupid thing you could ever. We are wasting our time. Because if a kid can learn French in France in 2 years, but clearly the way that we're teaching language in school is stupid, it seems to me. It's about time we learn that. However, let's discuss language. This is a fantastic thing. Although chemists were at the time limited by the timescale of flash lamps available, a race to study faster and faster reactions was just beginning. At a Faraday discussion meeting in Birmingham in 1954, called The Study of Fast Reactions, the German scientist Manfred Eichler, who is also a Hitchcock lecturer, I noticed, asked the Oxford Don Ronnie Bell how the English language would describe reactions which were faster than fast. Ronnie Bell replied, damn fast reactions, Manfred. And if they get faster than that, the English language will not fail you. You can call them damn fast reactions indeed. Now, it's very difficult to translate that into Japanese, I'll tell you. And when they tried it, they gave up. But anyway, let me just show you, because what language is here is a piece of Chinese. And if we look at the Japanese equivalent of this, some of you may be able to read that, okay? But the Japanese equivalent is this, which is the 3 monkeys. And the 3 monkeys in Japanese, which I can't read, but I've got someone to write, It has it has double meaning. It means no sea monkey, no ear monkey, no speak monkey. And so we understand that in Japanese there is a double meaning to it, and that explains this beautiful picture from Nico of the three monkeys. So language is very difficult, and to appreciate it, you really do have to learn the language. So if you want to understand Shakespeare, you really do have to learn English. And if I wanted to understand Akutagawa or some of the great Japanese writers, I would really have to learn Japanese. I can't do that. The same problem arises with mathematics. And here I take something, one of the most important pages in the whole of Bronowski's book, The Ascent of Man in that program. There was something endearing and personal about John M. Muldoon. He was the cleverest man I ever knew, without exception. He was a genius, in the sense that a genius is a man who has two great ideas. When he died in 1957, it was a great tragedy to all of us. And that was not because he was a modest man. When I worked with him during the war, we once faced a problem together, and he said to me at once, "Oh, no, you are not seeing it. Your kind of visualizing mind is not right for seeing this. Think of it abstractly. What is happening on this photograph of an explosion is that the first differential coefficient vanishes identically, and that is why what becomes visible is the trace of the second differential coefficient." Now, I think that's an important thing, because this guy can translate the photograph of an explosion instantaneously into mathematical language. Okay? Something that few of us can do, and certainly I could. And Bronowski himself could, because it went on. As he said, that is not the way I think. However, I let him go to London. I went off to my laboratory in the country. I worked late into the night. Round about midnight, I had his answer. It took Bronowski, who was, a pretty good scientist, till midnight. Well, John von Neumann always slept very late, so I was kind. I did not wake him until well after 10 in the morning. When I called him at his hotel, he answered the phone in bed, and I said, "Johnny, you're quite right." And he said to me, "You wake me up early in the morning to tell me I'm right. Please wait until I'm wrong." However, to show you what I mean by that, here is a mathematical relationship. And the question is, can one solve that? And the answer is, that's an equation that you have to solve every time you cross the road. Okay? That is what the chicken does. Even the chicken, if it gets to the other side, has to solve that equation. I think they've often say that jokes hit deeply at the culture. And let me show you this one, because I think this is really an interesting one. One of my great friends is John Maynard Smith, one of the best evolutionary biologists in Britain. And he had to write an article for a magazine, and the editor said, "Don't put any equations in it." Anyway, he wrote this, and he had to put an equation in, and he put this equation in it, and sent it off, and the editor rang him and said, "Look, John, you put an equation in it, this dx by dy equals a." He said, "Do you really need it?" And John said, "Yeah, I really do need it." So the guy said, "Well, look, can't you simplify by cross-multiplying the d's?" That's language for you, okay? I would hope that one day everybody that we talk to will understand that particular joke, because it hits the language of mathematics. The language of chemistry is interesting. For instance, this is a famous molecule. If I say C6H6 to a chemist, the chemist realizes it's a pivotal molecule in chemistry. Here it is. This molecule has 6 carbon atoms and 6 hydrogen atoms. An understanding of the chemistry of C6H6 is as important to an understanding of chemistry as an appreciation of Hamlet or Macbeth is to an understanding of English literature and Shakespeare in particular. It's a pivotal point in our culture. And it's, I think, in some ways more important, because an understanding of chemistry in the way that it's involved with the environment is important in the future. And unless our politicians, etc., appreciate that, I think we will have problems, because they do not. They just think, as some people think, that chemical alcohol and various other things. They're not aware of how serious they actually are. That's why we have problems. I'd like to finish with a few things which I think feel very strongly about. For the past 4 years, we have been trying to make science films for television. It seems to me if you've got, 100 channels and you've got programs which are just on golf, it is surely true that the scientific community should have its own channel. And we've been making programs with the Vega Science Trust. I'll show you the sort of programs we're making, discuss them anyway. And we do have a website, so if anybody's actually interested, I'll just point that out to you. And the view I have is that there are many scientists around who spent their whole life in science and are fascinated by this subject. And we're trying to make programs which are scientists and just asking them, how they got there, why they find it interesting, what's it about, rather than what one has at the present time in the public understanding of science, where media people, almost none of which are scientists. I come across this, I'm involved with BBC, the Horizon programs, the Nobel program that someone mentioned earlier, this scene. That was not made by scientists. There was not much science in it. There was very little science. Science, in many cases, in say the Discovery Channel, most of the time it's basically an eagle tearing up a gerbil and shoving the gerbil, bits of the gerbil down the throat of a little eagle. That's what, basically nature study is just animals eating other animals. That's basically what it is. And in Britain there's also most of the other programs are people making food, right? So if you're not watching animals eating other animals, you're actually watching human beings taking animals and making them into food for other human beings to eat. And that's only a small bit of science. Science is something else. And the sort of programs that we've made are individual scientists talking in lectures and presentations. One is on the origin of life by John Maynard Smith, Bill Bledper on the chemistry of interstellar space. That one is a lecture I gave. Akira Tonomura on electron waves, unveiled the microcosmos. A fantastic lecture, Japanese scientist, he starts off by discussing the fact that when you have iron filings around a magnet, you see the lines of force. And he asks the question, what are the lines of force like inside the magnet? And with an electron microscope today, you can look in thin films to see what is happening to the lines of force and the magnetic lines of force inside the magnet. David Bomford on Science and Fine Art, the way in which X-rays and infrared techniques have been able to unravel an understanding of artists of previous centuries, etc. Jocelyn Bell-Burnell, who discovered the pulsar. Kuniaki Nagayama on self-assembly, nature's way to do it. How does nature assemble human body and cells? Sumio Iijima, who discovered the nanotube. C60, when you elongate it, forms a tube, which I mentioned at the start of the lecture. And I think one of the most important is this on the epidemic of mad cow disease, BSE, in the UK. Now let me tell you something about BSE, because BSE is, we don't even know how dangerous it is yet. The problem in the 1980s, around 85 to 88, when a few scientists correlated the possible correlation between BSE, this so-called mad cow disease, with Jakob Creutzfeldt's disease, and also a disease in Borneo where a tribe used to eat the brains of their rivals, etc. And it takes about 5 years for this disease to actually manifest itself in cattle. But 60% of all cattle in the UK, probably here as well, are slaughtered by the age of 2. So 3 years before it would manifest itself, some of these cattle probably have this. And so it was in this food chain. It takes about 10 years to manifest itself in the human population. So if people are eating it in 88, 89, it's going to be another 2 or 3 years before we know how serious that problem will be in Britain. Now, my reason for making this program was not just because of that, but because I think this sort of problem is going to be the sort of problem of the 21st century, because long period induction diseases like AIDS, like VSE, and many others are the sort of things that are going to crop up. Nature is just picking away at us all the time, and things like this will happen. And it's the way that we, as scientists, interact with government that is going to be extremely important in the future, because one sees in 1988, when some of the scientists were worried about it, you talk to a government official and say, well, you know, we won't know for another 10 years. So we say, well, look, are we going to destroy $1 billion industry because you think there might be a possibility? And the question is, how do we as a society confront that risk assessment in the future? And I think that's going to be rather serious. That's one of the sorts of programs that we're making. And we've made quite a number of other programs, such as Nuts and Bolts of the Mind, Susan Greenfield, on the air about liquid nitrogen. There Ain't Nothing Nowhere, David Miller, about the fact that there's no such thing as a vacuum. If you have a magnet, it acts through a vacuum. What is that? And we find that we can talk to sixth formers, kids at school, 16, 17, about virtual photons, virtual particles. They don't have a hang-up about that. John Cornforth, How to Be Right and Wrong. We've got other programs by Helen Sharman, Life in Space, our first astronaut, talking to young kids about these things. And so we're trying to actually set up programs where we download a format to a scientist, say, look, what is it that you find so fascinating? And I don't want it to be interfered with by people from the media who think that they understand things and put form before content. I spent some time at UCSB, and I'm involved in their outreach program. Here in Japan, I talk to young kids, not in Japanese because I had an interpreter, and they enjoy science as well, have a good time. At Santa Barbara, here I'm talking to Hispanic kids about C60 and this giant fullerene, and they are involved in this, as I say, an outreach program where the kids come into the university. Instead of going out to the school, we have school kids to come in, they bust in, and then we make models of C60. Now, let me just tell you something about this. Some people have complained that C60 has got no usage like this guy at all. But in fact, these kids were silent for 30 minutes. All right? Every teacher in the whole country said this is the most valuable thing that we've ever seen. Anything keep this load of kids quiet for 30 minutes has got to be good. At the end of the day, the kids are really quite enjoy it and they're pretty happy. Here we see them sitting around making models of C60. Also in Britain, do the same thing. Here they are at Sussex. Jonathan Hare, who's working with me at Sussex in this school here, he helped them to make C60. In fact, that's local school. It's the first school, in fact, probably the third group in the world to make C60. Because you could make this at school. It's not a problem. You just get 2 rods of carbon, put a welder across it. And so, in working with this school, they were able to make C60 buckminsterfullerene. Not only that, they decided that they wanted a really big one, so they actually made this sculpture in their room. One of the kids decided to sort of do something imaginative, and here we see you can make C60 into a hat. I mean, this is the sort of attitude. Well, I got 2 other things to say. The first thing is that these kids, they're stimulated by, can be stimulated by science and chemistry. Here is one which I hope you can read. It's New Kid in Town. Hi, I'm diamond. I'm a kind of carbon. And so am I. I'm graphite. We're the only carbon types that are around. And then this is American culture. Wrong, there is a new carbon in town. Buckminsterfullerene. Bucky to my friends, I'm carbon too, you know. Can't be, he's round. He looks like a football. We're better than him. But then, can you do this? And Bucky bounces, and it's from Sarah and Lucy at the local school. So you can get kids to be stimulated to actually get excited about science and chemistry. 2 more overheads. I don't have any apologies. There's no reason for doing this except it's my favourite overhead of the year. I am an alien creature. I was sent from another planet with a message of goodwill from my people. The message says, dear Earth people, when you finally at last destroy your planet and have no place to live, you can come live with us, and we will teach you how to live in peace and harmony, and we will give you a coupon good for 10% of all deep dish pizzas too. Sincerely, Rob. Now, I really think this guy's my sort of guy, right? If only everybody around was like that, we would have a wonderful world. In fact, I just picked up a calendar. It's by Stein. Anyone who sees a book by this guy is something special. And as I say, I've heard. Anyway, I'd just like to say that it's been a very nice audience. And in fact, I think I've got one overhead, which is the last one, which somehow has disappeared. That was here. I zoom in. Okay, that's what C60 does for this little kid. It must be good for something. Thank you very much.
So, Professor Kroto's talk's open for some questions.
Is it all serendipity, or is there a special place that we should put our efforts to benefit from in the future?
I think it isn't all serendipity. I think there are as many ways to do science as there are individuals. The big thing is for you to do what you find is important. Okay? And I don't know how I do science, so how can I tell somebody else? Because some people I think are very good at, for instance, I think Japanese scientists are very good at focused research. I mean, anybody who can make a camera, a TV camera, that can sit in a stump of a cricket match, right? We've seen this. These guys are fantastic scientists. My work is something I'll discuss probably tomorrow. The discovery of C60 started from this molecule with carbon atoms. And I was just interested in the way vibrated and rotated at the same time. That was in the early 70s. Quantum mechanics and molecular dynamics. Then it went on to radioastronomy and discovery of these carbon molecules in space. And then thinking about that as to how they came about that it made these stars. And then it's a juxtaposition of Rick Smalley's tremendous technical achievement of taking a laser to vaporize carbon and refractory materials. So it was a juxtaposition. It was a serendipity as far as I'm concerned, but I don't think it was a serendipity in a more general sense, because someone would discover C60 within a year. It was my serendipity to actually suggest the experiment from space. So it's a double thing. Somehow discoveries are of their time. And this one had to be so. It should actually be discovered 30 years before. It was being formed in combustion plants. So as far as I'm concerned, I think my attitude is to do what interests me and not worry about what other people say is important. Because you never know how important it's going to be. In fact, I found something else, that the most mundane of experiments, you should just check it out, even if you think you know the answer. Because something nature really prefers to usually throw something else up. And that you learn from experience. When I first started, I thought, I better do something important, not so important for me at least. And then as time went on, I found that, there's something niggling away, and then a student would come along, very often an undergraduate in a project. And I think it's one of the most important things that we have is we have undergraduates who do projects, and they do something that's on your mind. It's not important enough to do with a graduate student or a postdoc who's going to get a job. What you discover, you do that project with an undergraduate. It's certainly much more important than you could ever believe, because you just check it out. So that's the way that I have done science, and not worry about what other people think is important. I don't know whether that's answers the question, but I would never tell somebody else how to do research. I think the worst thing the thing that I really feel bad about was when I was on the PSRC panel deciding about whose research was worthy of being funded. And I feel really bad because I didn't know, and we made a decision, an arbitrary decision about it. The only person who really knows whether it's worth doing is you as an individual. And if that scientist happens to have done some good work, give him some more money. Because the probability of they'll do some more work. And if you make a decision that it's not worthy, how do you know? You haven't done the background in general. So those are the sorts of problems that weigh heavily on my mind at the moment. Deciding who else is worthy of being supported. And I don't mind doing it. I don't do it anymore, actually. Is that an answer?
Yes, thank you.
With respect to your issue of symmetry.
Symmetry?
Yes.
Yeah.
In your view, is symmetry in nature, or is it an imposition of the mind on nature?
I think, but it's obviously it is in nature because the symmetry would exist whether we were not, whether they're not. But I think it must be also in our minds because we know that there's experiments in which the brain is triggered by horizontal lines, another part of the brain is triggered by vertical lines and other things. So I think it may well be, I don't know, I mean, the most interesting thing to me at the moment is the brain, okay, how it works, and pattern recognition is something that I wish I could start all over again and try to understand.
Well, certainly on a gross level, when you look at nature, there's very little symmetry.
Oh no, on a microscopic level it's huge.
Microscopic.
Yeah, but if you go to a large level, yeah, symmetry everywhere. Can I find something? Probably not.
So it's all man-made.
No, it's not. No, I don't think so. I don't know whether, I certainly am not sure whether, I may just be able to show you that I probably didn't bring it, unfortunately, the wrong overheads. No, I think you'll find that, for instance, the geodesic domes as an example, you might think that's man-made. If you look at the eye of a fly, you'll find that it has built on the same geodesic principles, that you find a hexagonal network, and then as it curves. I mean, I'll show some examples of this in Nature probably tomorrow, my next lecture, because you find the symmetries there. On a larger scale, it's just a building up of these things. I mean, there's this huge symmetry in DNA, okay? Brilliant symmetry. And in fact, we just made a film, this is the most wonderful film. I may bring slides tomorrow. If I have a laser pointer, I may show something quite spectacular. Just as a final example of the way that you can use a laser pointer to show how the DNA helix, double helix was unraveled on X-ray structures, and you can do this very simply. So deep down, there's obviously chaos, but the question I was asking, I think, because I don't know the answer, questions are more interesting than answers, is why are those kids so enthusiastic about this beautiful symmetric object? Okay? And I think it does focus on your question. And my guess, a guess is maybe, and that's something I've wondered about, is it because it is a pure sensation in the mind? Because if it's true that, as I think it is, that all our perception is a convolution of various symmetric patterns, you put them all together to see the complex world around us. The simpler this is, perhaps the more pristine the psychological effect is in the brain. And it may be something to do with that. I mean, after all, we listen to music and we hear chords which are symmetries and, really rather nice symmetries that doesn't give us tremendous buzz in my music. The same is true of poetry, So somehow those symmetries are around us, and the more symmetric, perhaps the simpler they are, the more we enjoy them. And then as we get more and more understanding these things, we might have broken symmetries a bit better. These are interesting questions we can talk about, but I don't necessarily know the answer. But it's nice, the question is better than the answer.
What's the consequence for your science that you found this physics
That's a very complicated question. The discovery, I'm as surprised as anybody that I ended up at this practice. I mean, I used to say that for the start. I mean, I used to say, Nobel Prize winner, there must be smart guys, but some of them are. And some of them are very lucky, some of them are very clever, and some of them are the brightest and cleverest people I know are not going to get the prize. That's brilliant science I've ever seen. I was very fortunate I think I'm a reasonable scientist. I've done work which I'm more proud of scientifically. The molecule C60 is to change our view of carbon, perhaps arguably the most important element in the periodic table. Its way of bonding is so vital to the way that we are ourselves. Okay, so it's shown something that we should have seen a long time ago. Okay, so the first thing is change our perception of carbon and the way that sheets material can actually structure into new materials. The future is very interesting. The tensile strength are about 100 times that of steel. Okay? Because of these nanotubes, which I'll talk about a bit tomorrow, but more on fun. And they are conduct like metal. So the probability of using these and making aeroplanes which are 20, 30 times lighter than present aeroplanes is on the cards. We can't control the formation of this material yet. But the material exists. It self-assembles. We have now, in microgram quantities, materials with unheard of tensile strength. We've done the easy bit. We discovered that they can form. And the hard bit is to make it in perfect yields in tons. Okay. It will then revolutionize civil engineering if that can be done. I don't know whether it can. I think it can, because unheard of strides have been made in the last 20, 30 years. It may take 20, 30 years to get that material. So those are revolutions in materials. The initial revolution is in our understanding of carbon chemistry, and we should have known. It's so obvious now that these materials, these cages can form. Then you asked another question about me personally, about my science, did you? Did you?
Yeah.
Well, it's had a lot of effect on me, because people ask me to give these lectures, and unfortunately I accept them. We're still carrying on material research, but one of the major things I want to do is to British television, and also here in the US, is to try and get a science night on television, at least one night of science, talking about science, without interference from other people who think they understand science better than we do. And I think that's very important, because I think the problem with science is that people don't understand it. We're just as much a cultural community as any other. So those are the sort of things all involved in answering that question. Yes.
Would you comment on the growing number of partnerships between corporations and universities, for instance, Microsoft Corporation in Cambridge, in England, and how this might impact both the secrecy and versus publicness that you were talking about research, and also the questions that scientists ask? And can you comment on that?
I couldn't quite hear it. Was it to comment on the interaction between industry and universities on research?
Yeah, the funding and the
Yeah. I think the important thing is to fund research at every possible level. And I think the problem is that funding now is becoming more and more difficult, that people like myself perhaps wouldn't be funded in the future. And I think there are a large number of really good scientists who can't do it any other way. So I worry about the young scientist who's coming up today in university, who's just fascinated by the way it is. And in the past, were able just to probe nature and what was interesting to them. And that sort of research is becoming, it seems to me, becoming more and more difficult to do. And certainly it was the case when I was on the EPSLC. I felt that the way that I would like to support people, I wasn't able to do it because I was just one voice amongst many, was that there should be obviously targeted research. I mean, there are major problems. I mean, that's one end of applied science. We have major problems to solve. But there's another area where those solutions,
come out of left field. I mean, as an example, I think, is liquid crystals. You know, liquid crystals, like you ask someone who doesn't know and say, well, look at this display. It actually has revolutionized much of our lives. There's a lot of displays now use these on computers and things like that. But the first liquid crystal phenomena were not 20 years, not 30 years, not 50 years, but over 120 years ago, Rice was studying the way light passes through liquids. For that to be understood, it required an understanding of molecules, optics. It went all the way through then the development of transistors and semiconductors until we got to the crystal display, and also synthetic techniques to develop molecules that could behave in electric fields and could orient in a way. So if you said to someone 120 years ago, we want to produce a display in 100 years' time, it's not going to be funded. I'm worried that there are a lot of young scientists, people who are imaginative, who can't work in this way in industry or in the scientific research, and they're not going to be supported. And I see it more and more difficult, it being more and more difficult. So the way that I'd like to see university research funded is that the budget be split into 3 bits. And the first bit is given to young scientists to get them started. The second bit is given to give some money to a guy whose last 2 or 3 or 5 years research has been really very good, and to split the other one into a little bit more parsimoniously amongst groups who did pretty well a few years ago, not so well, to keep getting back on the track again. And forget about what the research is, because that's, it seems to me, is what it is we should be doing. Who should be deciding what is important is not government. Government should be supporting education and research for the 20th, middle of the 21st century. Industry should be focused on what they want, and if they don't know, and they're not supporting funded, why should government fund it? They don't know. So they're going to do that, and I think that's what's happening for it. So I think that government is focusing on trying to shore up industrial research, and that's not its job, and it doesn't do it very well, and it doesn't particularly poorly in Britain.
Maybe one last question? Okay.
The news media this last week reported that the science and math scores of students in America are much lower than other countries. Could you comment on this?
Well, it's probably correct, but we've got so many more of them that it probably doesn't matter. We've got market share, so we've got this huge number of people going through with this tremendous number of people doing research. So if you've got 80% of the market, why you don't have to worry, because you've still got plenty more than anybody else. But it's probably true, and part of the reason is that, I look back at my youth, and I was brought up at the end of the war, and life was tough. My parents were refugees. And I didn't have television, and I didn't have computer games and all these sexy things to play around with, and I had to work really hard. And you now do a lot of the things that I think people are doing in public understanding, getting kids turned on. They're standing on their heads and jumping through hoops to make kids excited about science. And when they come down to it, they've got to learn differential equations and all this other stuff. They've got a real problem. So I really that what you should be doing is really having really boring lectures, right? And the guys that survive those, they're the ones who are going to actually be very good. I worry about this tremendous effort on educating and getting kids excited about science when you really have to do the work. Okay? That's something that I think maybe, one is a whole some philosopher, but that's certainly something that worries me. I look back at my notebooks and I say, gee, I must have been a boring, turkey kid to actually do all this dichromates and all this stuff, which looks not very exciting to me today. And certainly wouldn't look exciting to someone in the first year of university. I had like an hour upon hour upon hour of group analysis. How many people? But the older chemists did all that stuff. They don't do any of that really tough stuff. And that developed, some determination. And I worry about that. So, I think modern kids have got too many exciting things. They want to be rock stars and they want to be cool, man. The I saw in Santa Barbara, and I've done this with 9-year-olds, it's very good. With 14-year-olds, it's really fun. And it's not cool to be a scientist or to be very good at mathematics. It's much cool to be a footballer. And I think that's part of the problem here, I suspect. Whereas in other countries, maybe, they see science and technology as a way out of slavery type existence. Whereas here, everything is so easy. That's only a worry. I'm sure there's some of that there. I'm just a homespun philosopher on that one. But I think in the end, the USA's market share in research and other things is the one that will make it very difficult for other countries to compete. It's a problem. If you do 80%, I don't know what it is, I suspect it does over 50 to 60% of all the research in the world. Good research. And all the best people coming here, right? We've got a huge number of people from every country, and they're inputting their ideas into it. So that's, as far as the country's concerned, it's okay, but the youngsters, they're just going to live off the fruits of other people.
Okay, let's thank Professor Kroto again.
I assume that you're aware of, but in case you're not, a motion picture that puts forth your paradigm very nicely is an old one by Alec Guinness, where he is the inventor of a non-destructible suit.
Oh, yes.